For those of you who don't know me, my name is Daria, and I work for EPAM Systems. And for today's work group activity, I'm representing one of the AI arms, which is part of products that we have as EPAM. And it's a GenAI cohort and concept set generator that I'm going to be showing today together with our Prometheus tool. So a few words about the technical setup of how it works, because I guess that's a question that usually comes up first. And basically our GenAI cohort and concept set generator is a containerized Python backend service with REST API. So there's also a relational database with vector store, so it allows you to do a semantic vector search of OHDSI concept vocabularies. Containerized basically means that it's easily deployable to any infrastructure that has Docker containers technology. And the Python backend service is written in Python language, and it can be delivered with UI or without UI. So basically it can work with our Prometheus tool, it can work with Atlas, or it can even work without UI, or be attached to any kind of UI that somebody else may develop. So it's a standalone tool, and that's basically what I'm trying to convey. It utilizes cloud provider tools, so whatever is available, whatever model, LLM model, is available in AWS Bedrock. So the hosted LLMs, we can connect it to be using the hosted LLMs inside the AWS for generating concept sets and cohorts. So we as users submit a free text prompt, and we are able to generate either concept sets or cohorts through the integrated application. So this is basically how it works. For today, what I'm going to be showing to you, we're using currently with our tool, with Prometheus, we're using Anthropic's tool, Sonnet 3.7. We've tested multiple models for precision and productivity, and we as a team have come up to the conclusion that Sonnet 3.7 is the model that currently performs the best. We also have a team of scientists who are epidemiologists, data scientists, who do a lot of cohort validation. We create human-made cohorts and GenAI-generated cohorts, and then we compare the results so that we can continuously create tool improvements. This is just a quick overview of the interface that is available. And sorry?
The slide didn't advance online.
Oh. All right, so if the slide didn't advance, what we can do the actual demo, so you're going to see it on the tool. So let me just close the presentation. Let me just share my screen instead. And hopefully that works. So let's go straight to the demo then. So for today's presentation, I took the liberty to create several code lists. None of these code lists are from the list that we were creating today and the ones that we were competing on. So it's a different example. It's a gastric cancer that is limited to cardia of the stomach. And I'm going to be showing to you different options that are available to you or anybody who's using this tool. Basically, here's code list number 1. And this is a code list generated by AI. When we click regenerate, we can see the user interface that allows us to work with the generation. You need to insert a name, you need to insert your prompt. It's a free text. You can either drop some clinical ID and name, or you can input a longer prompt with a little bit more instruction on how do you want it to be generated. There are optional filters available to you. You can pre-select one or multiple domains that you want to restrict the output to. You can decide whether you want the output to be standard, non-standard classification, or everything that it can possibly generate. And you can pre-select different vocabularies. So you can basically generate standard, non-standard concept sets, or the ones that are limited to only certain vocabularies. There's also new functionality that we just introduced literally last week that has to do with the precision of the search. So if you select exact match, the first thing that Prometheus GenAI is going to do is going to look for exact match of the text string of clinical ideas that you insert in your description prompt. And if it finds the exact match, then that's what you're going to get, along with all the descendants. If you want a more broad search, you have options to change the precision with a few options. So you can, bear with me. You can change the precision and allow your LLM to search your text string along with 5 closest vectors. So similar clinical ideas that chances are very valuable for you because it's going to look at closest hierarchies that are available, and then that will give you a broader description of clinical idea. And then every next option essentially allows you to broaden your search to 10 vectors or 15 vectors in terms of your concepts. So you can imagine that every time you go broader, you're going to get a much larger concept set that will probably be able to catch everything you want, along with a lot of things that you don't want. All right, so this is the basic idea. So we can look at our first concept set, which was an arrow search, which we were asking for either a full text match or the closest possible, most restricted output. So you're getting 13 included concepts, and you can see that, let's review together the prompt that was given. We wanted a concept set of all gastric carcinomas of all histologies, but limited to the cardia section of the stomach. And this is the code list that we were able to generate using our GenAI. What is nice and what I absolutely adore is that you get the generative AI report, where you can track what was the reasoning behind creating this particular code list. So as you can see, the GenAI engine analyzes the prompt, deciphers the clinical ideas, parses them, looks for synonyms, looks for the similar ideas, assesses the vectors, creates a candidate code list, and then kind of evaluates each concept in the candidate code list based on the relevance of the name and relevance of the domain, and gives it an overall score whether this should be included in the resulting code list or not. As a result, after all the creation and filtering, it will produce the final output in a form of a JSON file, which can be downloaded from here, or you can actually see the expression in the expression tab along with all the included concepts. Currently, the setup is such that it automatically turns on the descendants. So as you can imagine, if you wanted to exclude certain things, you can only exclude it based on its reasoning, not based on the hierarchy, which is current limitation, which we're probably going to see as the result of our comparison later on. But basically, this has been built with the idea of a productivity boost. So it was never meant to replace a human interaction, but it's an augmentation of a human scientist, which allows you to gather the draft of a concept set that you later can evaluate, you can later assess, you can later regenerate based on the narrow or broad definition that you would like. There is another portion to this that does not participate in the competition. That's a big disclaimer, because we felt like this goes against the rule of no human in the loop. So basically what we submitted for the competition is just a prompt generation, which you see here in a JSON file, the results from it. However, as a user, you also have access to suggested by AI functionality, which is the second step that you would usually go to. And suggested by AI uses the same prompt, or you can change the prompt here. And what it's going to do, it's not going to search its knowledge base. However, it's going to search the scientific publications for codes that have been used by other people to create a similar code list with the same clinical idea. So here, as you can imagine, most publications will not be using standard SNOMED, it's going to be using ICD codes, although sometimes it does generate SNOMED concepts as well. Here, in our case, we have generated a list of codes that could be candidates for our code list, concept set, and each...
He just said you're wrong.
Oh, and each concept, you can see where it's coming from. So there is a reference list of all the publications that have mentioned this particular code as a good code for your clinical idea. And you can go and check that those are real publications and not something that it hallucinated. So this is nice. You can basically take it as a next step as a human to see if everything is included in your candidate description, or you can find some new codes that are suggested by literature. If you're building a standard code list, you will go and see what C16 is mapping to in terms of a SNOMED. We also have the functionality where you can do an automated mapping of all the non-standard concepts to standard if you'd like, and resolve the many-to-one or one-to-many mapping. So this is basically the idea. Just to show you an example of a broad search that is the maximum 15 vectors that the GenAI is going to assess. So as an error search, we got 13 included concepts, and as a broad search, we got more than 200. So you can imagine that it's a lot more broad, so you're probably getting a lot of false positives. However, it may fit your clinical needs to assess everything that is out there and see maybe there's something that interests you as a clinician. So this basically completes the idea of how we generate concepts. I wanted to take a quick 30 seconds to also mention that we are able to generate cohorts. And this is an example of a cohort generation for lung cancer diagnosis, where you can basically copy-paste a portion of your protocol with all the cohort logic that you have for that cohort, along with index event, inclusion, exclusion criteria. You will be able to parse and understand that logic, build all the concept sets for all the clinical ideas that you mentioned here. So here are all your concept sets, and build the actual definition in the cohort builder. So again, it saves you a lot of time if you are working with definitions that have dozens of inclusion, exclusion criteria. This gives you a really good draft to start with. So please, if you have any questions, I will be happy to address any.
All right, so we have 4 AI arms, and now we have seen Daria, so we're going to rotate to the next one. Nico, why don't you come join and introduce yourself? I'm going to...
Hi everyone, I'm Nico. I'm from King's College and Lang's Teaching Hospital, working as well on agentic workflows with FastOMOP, where we try to ease the access to OMOP databases. And all of that involves concept reasoning as well. And that's why we came up with that to ease the process for concept set creation as well, because we get accustomed to having it easier than we had it before. Of course, Atlas is a great tool, but it's complex to navigate, and we want that ease we get accustomed to with ChatGPT and the others. So this is a little bit of the research perspective, so what's behind that reasoning component for medical concepts. And there are mainly 2 components involved. First is you need to break down the process which is involved in concept reasoning into achievable subtasks, because LLMs are limited in the complexity they can generate in one go. So you'd try to come up with subtasks for that process which are achievable in one go. That's how we broke that down into 5, maybe 6 different subtasks which are executed one after another. And on the other hand, perfect. So the breaking down in subtasks is one side of the question. The other thing is you need reliability and not hallucinate. So what we've done is basically what others do as well, build a vector database which you can query, which you can rely on, and we included all of the OMA vocabulary relationships as well, because for medical concept reasoning you need that finer or coarser, etc. So we try to have a hybrid approach where you can get similarity, and that's the first thing. Up there you see the different terms, right? So you match based on semantic similarity, on synonyms, how it's spelled, maybe misspelled, maybe you'd have abbreviations, acronyms, etc. And then you'd want to disambiguate between the terms, and that's where the relationships come into play. And you'd have the different relationships which you could use for sanity checking and for traversing from coarse to fine-grained. So, for example, systemic lupus and the drug-induced lupus, as for our concept set creation today, these are related, right? So you can traverse from one to the other, and the LLM can do that reasoning as well and see, okay, maybe it makes sense to include this, or maybe it doesn't make sense to include this. And what you end up with is, if you have all of these tools available, you try to fine-tune the LLM, or to give the LLM the context and the heuristics to navigate these complexities. And once you have like the reliable database with all that information stored and the right heuristics, that's how you can get there. And just a very quick non-live demo, because it's locally executed and takes a long time to execute at the moment. If you do API calls, that gets way faster. So basically it gets the same information we get as humans when trying to create the concept sets. Then it will reason with some literature involved and some RAG-based retrieval, and come up with extracted entities and with how to combine these entities into a concept set. And then for each of the entities extracted from the vignette, it will perform similarity searches, and then that's the important step. It will apply relationship reasoning. So it will traverse the knowledge graph to some degree, going up and down, and as well for causal relationships, which are stored as well in the OMA vocabulary. You can traverse from them and see, okay, this medication might cause this side effect, or this procedure is often involved when trying to come up with diagnosis.
So, can I ask you?
Yeah.
So when it does it, it's only using the ontology, or is it using also the semantics?
Semantics and ontology, yeah. So it's a hybrid approach of both of them. Yeah. And then you get all of these different extractions, and in the end you'd perform a sanity check, which is in this case failed, because it included a concept which might be downstream not to include or to exclude. And then in this case you could say, okay, with that, go again, exclude more, include more, or pass it back to the human. And you'd get on the side here the concept sets as JSON for importing to Atlas.
And when you said the rubric, is that the context that you put in your prompt? Like when you said you had in your slide, there's a rubric for the reasoning part.
Yeah.
Reasoning, like you add a rubric that you would get.
Yeah. So these are instructions for the LLM as prompts, yes. But with some tool calls involved. So all of that is built on Agno agentic workflows, where you can combine like just prompt engineering with tool calling, and so you combine these two.
But it's pre-set, like you put it as part of the inputs. It's
Yeah.
not in the loop, is it? But at least it's as, it's not like it's coming back to you and then you give another.
Yeah, we've been experimenting with that, and we had this discussion at our table as well. So basically it makes sense, if you want to use that on live databases, to give it the feature of querying what concepts are actually in the database and what difference it makes. So these feedback loops you can build into that as well. They aren't currently, but you can do that.
But ideally you want to do everything up front, so we can automate like a process where it doesn't include.
Yeah,
But I
well,
see the
the,
value
the,
of
the thing is, yeah, normally you want to have it as automated as possible, but of
Check.
course you need to have the sanity checks to make everything. Yeah.
Beautiful.
Yeah, thank you. That's it so far.
And I said I was going to give Nico a little bit of a hard time. He thought the submission was tonight, after the OHDSI Symposium. And so yesterday I had to remind him at 7 o'clock at night, and so he ran it on his local computer, all the LLMs, without the power of, I guess, the cloud computing environment. So this is a locally run at 7 o'clock, and it's submitted about 2 o'clock in the morning?
Yeah, it took some time, but it is.
From our side.
No, I think that was my fault.
Is your code open source?
It's not yet online, but it will be open source. Yeah, yeah.
You good?
Oh. Are we? So in the interest of time, let me just make sure. Yeah. So in the interest of time, you all heard me talk yet. You can hear me, right? You all heard me talk yesterday. I could, I don't have to go through the presentation again. If there's any specific questions, I could show you the prompt that I use. I could show you the output that I get, just from open source standpoint. This is open source software. I haven't published it yet to OHDSI. The only thing that we do is J&J uses a licensed version of OpenAI, and we point to that. Within the software, you'd need to specify where you're going to point to. You need some sort of source that you can use, that you can do API calls to the LLM, which I understand is not that hard. I think I pay $20 a month personally for OpenAI, and I think that gives me API calls to them. So just to start things off, we could just show you the prompt that I use.
So could you, for people who were not, everybody aware of the tool? Okay.
Yeah.
Yeah, it was one of the lightning talks yesterday.
Yeah, I could go through a very quick.
Yeah.
Let me just go through a very quick PowerPoint. I have a short version of yesterday. What has there double? I don't know. Just get this out of the way. I don't know why that's there.
You just have to go to the next page because you pasted it by accident.
Oh, maybe. Oh, okay. Yeah. So just this goes through the steps in the process. What the first thing I do is create a list of actually, I'm going to stop doing this. I'll just do the better one because this has a better version of it. The steps in the process are probably important. And let me just do this and this. Okay. So the steps in the process for this tool is you define a clinical idea, for instance, myocardial infarction. And then you find a starting SNOMED concept to start with. So for acute myocardial infarction, there's a SNOMED code for that, 312327. Then, this is all outside of the LLM, it creates a list of the starting concept, all its descendants, and what we use, which is a little different from the other two presentations, we use Phoebe, the recommender system that's usually attached with Atlas, as the method to get things that may not be the concept and its descendants. So it uses a bunch of different ways to do it, lexical searches. It does by patient context, things like that. So it creates a long list. And one of the things that we were trying to do, one of the reasons why we did this is creates a very long list, which is difficult to wade through, but also for non-clinicians, when it shows you something that, you know, it suggests, and it's just like, well, okay, maybe. If you're not a clinician, you don't really know. And that's, you know, so we create this long list, and then we prompt the LLM with each concept in that list that came out, that, you know, that was recommended. Either it was the concept itself, descendant, or from Phoebe. We then ask the LLM to specifically choose which suggested concepts belong in the main concept, and the criteria that we use is that if we ask the LLM, do greater than 95% of the people that have this concept, the suggested concept, also have the other concept. So for example of coronary occlusion, we would ask, do greater than 95% of the people with coronary occlusion have myocardial infarction? So is it subsuming? Does myocardial infarction subsume coronary occlusion? From there, we create this, we look at all the ones that the LLM said, yeah, you should include these. And then we take that new list, and we take those and their descendants, because there may be some new ones added, and we send it to we send all the ones that we haven't questioned before, the new ones, to the LLM for it to adjudicate again. And then from there, we create a final set of all the ones that are greater than 95% should be included, and then we post everything to Atlas. Yeah, you don't have to hear the experiment. So that's the clinical idea. That's not the clinical idea. That's the process idea that we go through. Let me just show you. Let me just show you an example of a prompt. So at the end of the process, the LLM produces these set of artifacts for each condition that you look for. So this is for deep vein thrombosis. So it gives you the clinical description. It gives you a clinical description that we use. We have a format that we use for clinical descriptions. It gives you the JSON file, which would be what you could then import into Atlas if it imports it for you, but it also gives you a copy of it here. And this one here gives you all the concepts that it went through and the rationale on whether it said to include it or not include it. And this one here it gives you the text, it gives you the prompt of the final one that it checked. It was the last one it did. So let's just go through a little bit of that prompt. You can see that pretty good. You know, typical, you are a medical expert, your primary function is to do this, blah, blah, blah. And then it says, so here's your data analyzed. Proposed concept is, in this case, myopathy due to systemic sclerosis, and the specific condition is systemic sclerosis. And then it gives you the idea to be able to put in any of these excluded criteria, which was, for this one, it was a whole bunch. Then it includes the clinical description, some other context there, and then it asks the real questions here. It says, you will estimate the proportion of patients with myopathy due to systemic sclerosis, that's the suggested concept, who also have systemic sclerosis, the main concept. Selecting a proportion category, and this is the methodology we're using. We're having it do proportions of who has it, and this ubiquitous is the one that we're doing. That's the winner. One of the things we learned from this is that we took a conservative approach, and we say we have it, and whether it makes a difference, it seems like it makes a difference. We did have it go from worst to best, rather than the other way around. So it's not just looks at ubiquitous as, yeah, that's great, that's the one. So we have it be very conservative and start doing it in this order. Then it asks the question and a couple other things there. So that's the main thing that it does. And then I have it produce a JSON file at the end that asks a specific set of questions. What I found that was very interesting is that the order that I ask these questions in at the end actually makes a difference in accuracy. You switch these things around, and so I'm asking things like, I have it provide a definition of what the suggested, what are the proposed concept. I have it give a definition of what the main concept is. Just to sort of, I don't know, whether it just sort of keeps it in its mind correctly, and what the definition of the exclusions are. Then a couple other things and then I ask the question, is the new concept in the excluded list? And it answers that one. And then so I do it. I ask, is it in the excluded list? But I also have it give an argument on why it's in the excluded list. So a lot of these things, I wanted to answer a question, but I also wanted to give a rationale on why it's doing it. And then finally, at the end, it gives the final answer. One of the things that you can see, let's see, do I have any? Yeah, acute myocardial infarction. So this is the output that I get. This is, so each idea is passed one at a time. I use R. One of the things we did find was that with the LLM, have it do as little as possible, or the things that it does best. Do everything else outside the LLM. Don't ask it to create tables or put things together, sort things or whatever. So for this one, here's the suggested concept. So acute myocardial infarction. The suggested one is acute ST segment deviation, elevation, myocardial infarction of inferior wall. This is the concept ID. This was the main condition, and the final answer was ubiquitous. So this was one that should be included, and then it gives the rationale. The proposed concept, acute ST segment elevation, myocardial wall, inferior wall, is a specific subtype of acute myocardial infarction. By definition, the presence of this concept implies the presence of specific condition. Therefore, the proportion of patients with the concept who also have the condition is effectively 100%, making it ubiquitous. So it goes through that whole thing. Yep.
What does latency look like on this if you're passing each concept in as a prompt? I know you said
it probably takes, for each concept in our system, which I'm not sure how fast it is, it may take 3 seconds or so. Yeah. For some reason, and then they give us a fee for that, because even though it's internal and it costs like half a cent. Yeah.
What data is it referencing for your 95%?
Yeah, that's whatever it was trained on. So it's no specific medical terminology, up to date, right?
It's whatever OpenAI
Yes.
trained on.
Yeah. So it's the existing state of the literature. Some of the other groups here we're talking about. I think over in Oxford they're talking about having it use some medical terminology, or actually I guess they have up to date, or the equivalent of up to date over in the UK.
When Nico presented, it's using the ontology of OMOP itself. So it uses relationship is
Yeah.
so it's not having the percentage, but the vocabulary itself is a knowledge graph, and it's using that to make inferences as well.
Yeah. Yeah. So we're using. Sort of subverting that or speeding that process up by using Phoebe, which does something similar. So we're just getting the ones that to get the pass in there. Yeah. Yeah. One of the things we've had, our original plan on this, just to pass on, is that we were going to do co-site similarity using that method between different concepts. And that did not work very well. However, they get the values for one concept. It just didn't fit. So that gave much poorer performance than this. Much faster and it's cheaper, but didn't work as well. Yeah.
Are there examples? Maybe I'm not understanding. Are there examples where a suggested concept was classified as not really synonymous with acute myocardial infarction. And I'm actually looking at coronary occlusion there,
Mm-hmm.
and at least wondering about that. But again, what would there be an example of something that is not?
Yeah, so let's, let me just, so these were ones that were deemed common, and if you remember that, that was, I don't know, 10 to 90% or whatever we have here. So in this case, ones that, so remember, all the concepts we get are either descendants of the original one, myocardial infarction, or Phoebe has suggested it. So based upon some of the characteristics of Phoebe, this recommender system, it suggested acute coronary bypass graft occlusion. And for that, it says coronary artery graft occlusion does not logically imply myocardial infarction as a synonym or subtype. While it is a risk factor, it is not guaranteed to be a result of AMI in all cases. Therefore, this category is not applicable. That's where it's looking at the ubiquitous. Yep. So this was one that was suggested to it, and it said no.
Give the reason of no.
Again, maybe I've missed this, but I'm just, for example, sepsis, it could be a complication.
That's right.
For the patient, but what is actually the prompt asking? In other words,
Right.
I'm
So
surprised that it is even. I'm just, what is the prompt asking? I'm
yeah.
surprised.
So
It's even,
yeah. So the tool Phoebe, which is outside of the system, but what we use, uses a bunch of things that to be able to pull stuff in. So one of the things it does is I think cosine similarity with other things that are happening at the time of myocardial infarction. So probably a large proportion of, or a significant proportion of people with myocardial infarction have sepsis somewhere around the time of their myocardial infarction. So based upon that analysis that Phoebe had done to say, we don't know whether it's a thing or not, but you might want to consider sepsis because most people who have myocardial infarction, or a lot of people who have myocardial infarction also have sepsis. So that's why it was a suggested concept.
oh, okay. So the suggestions are coming from Phoebe?
Phoebe, yes.
Okay.
Yeah.
And,
So it's, yeah.
but I'm just a little confused in the sense that the classification is intended to identify things that are exactly acute myocardial infarction or things
Yeah,
that
so
can
the
occur
prompt-
with acute.
Yeah, the prompt for this process is asking it, what's the probability of someone having that diagnosis, having
Okay,
also
so the
myocardial
prompt
infarction?
is essentially saying, how common does
Yeah.
this co-occur?
Exactly,
with
correct,
blah, blah, blah?
exactly.
Yes.
Exactly.
Yeah, so to greater than 95% of the people with sepsis have myocardial
I
infarction.
just didn't get that.
Yeah.
Yeah.
Which is kind of how clinicians think when we give them a list and tell them, like, we want to identify with myocardial infarction. Is a person with this case would be legit. So they kind of think of, like, what's the probability of the person with this code also having infarction?
Yeah, so, and it works for things that are, sepsis and myocardial infarction are obviously two different events and not everybody has it. One of the things that we found that we were looking for the concept of the condition of nausea, and the humans didn't include the word, the concept for vomiting, but the LLM said, 95, greater than 95% of people who experience vomiting have nausea. So if you want to have an inclusive look for that, and that which is important from a signs and symptoms standpoint, because because they're not always well documented within the observational data. So for something like if you're looking for nausea, you might want to include vomiting because maybe they didn't put down nausea, but more than 95% of the people with vomiting have nausea.
Another question, if you don't mind.
Yeah.
The way that SNOMED, et cetera, works, some of maybe not this list, but prior are descendants of acute myocardial infarction.
Yep.
So essentially, by definition, they are. So it would be also interesting to see, or maybe you've already done this, what sorts of things are showing up that are not descendant.
Correct.
Yeah, so that's, yeah, so coronary occlusion is not a descendant.
Another way,
Yep.
things that I'm wondering how to interpret something where it is a descendant, but the frequency is
Right.
common or rare or what have you, how to think about that.
Yeah, so a couple things that we found with that, and, this is all new and sort of experimental. Some of the things that we found with that is that when it excludes a descendant, it's generally because sometimes it's because of a poor mapping within SNOMED. The other thing is that this allows you to do exclusions. So sometimes the descendants might be in the excluded category. So while so it does check all the descendants. It doesn't just include them all automatically. So a couple reasons why there wouldn't be descendants. You want to move on? Okay. Thanks.